Good evening, class 11. Let's start. Today we are going to discuss relationship between Kp and Kc. So Kp is represented as this. This we have done in the last class. Um, this one. Okay, this is the relation of Kp. This is applied for gaseous reactants and products with respect to their partial pressures. Now, assuming ideal behavior of a gas, we can write PV equals to nRT. P equals to N by V RT. Okay, N by V is written as concentration. Okay, it is moles per liter, so it is concentration. Right, now we are going to represent the partial pressure in terms of the concentration over here. So Kp I can write it as Pc. Pc I can write it as concentration of C to the power A, RT to the power A. Pd also similarly, concentration of D to the power B, RT to the power B. Then the denominator, concentration A to the power alpha, RT to the power alpha. Next, Pb written as concentration of B to the power beta, RT to the power beta. Now this small a, small b, alpha, beta, they are the respective stoichiometric coefficients. We could have taken some other stoichiometric coefficients also, like small a, small b, small c and small d. Right, that is our choice. So this one. Now we will be separating the RT term and the concentration term. So Kp equals to what? Kp equals to C, box C to the power A, box D to the power B, then box A to the power alpha, box B to the power beta. And RT we are writing it as RT A plus B minus alpha plus beta. Okay, this one. Now this term, this concentration term is what? This term is my Kc, because it is the ratio of the concentration of the reactants to the products. Ratio of concentration of the products to the concentration of the reactants. Okay, and RT, this is A plus B minus alpha plus beta, which is written as delta N. Delta N is what? It is difference in the number of moles of gaseous products and gaseous reactants, or I can say it is the difference in the stoichiometric coefficients of the gaseous products and reactants. So this is my relation between Kp and Kc. Now we have three conditions when delta N equals to 0. Delta N is positive, delta N is negative. We are going to show it by examples. When delta N is equals to 0, Kp equals to Kc. Example is this one, H2 plus I2 reversible to Hi. All of them are in the gaseous state. When delta N is positive, Kp is greater than Kc from this particular relation. And example is this one, PCl5 reversible PCl3 plus Cl2. Here also all of them are in the gaseous state. Then only we can represent the Kp and Kc relations. Delta N when negative, then Kp is less than Kc. Okay, so here the example is your Haber's process, where nitrogen, hydrogen reversible to ammonia. Okay, so these are the three equations where we are using three conditions of delta N. Delta N being 0, delta N positive and delta N negative. Now, next we will be doing characteristics of equilibrium constant. Now, equilibrium constant is independent of initial concentration of reactants and products. It depends on temperature. Next, if an equation is divided by a factor 2, then the new equilibrium constant becomes equal to the square root of the previous equilibrium constant. For example, if I take this equation N2 gaseous to ammonia. For this particular relation, for this particular equation, if I write the expression of equilibrium constant, that is Kc, this one with respect to concentration term, N2 and H2 to the power 3. Now, if this particular equation I divide by the factor 2, then half N2, 3 by 2 H2, reversible ammonia. Okay. Now for this, if I write Kc, now this is my Kc dashed. What do I get? This is NH3. Then this is N2 to the power half. And this is H2 concentration to the power 3 by 2. Now this particular thing is nothing but it is the square root of Kc. If I square root this term, then only I get this particular expression, right? Next, if a particular reaction is, if a reaction occurs in more than one step, overall equilibrium constant is equal to the product of the stepwise equilibrium constants. If I take this two equation, N2 plus O2 reversible to NO, if this is my K1, all are in the gaseous state, and this one is another 2NO plus O2 reversible to NO2. Here also all are in the gaseous state, and this is my K2. So overall equilibrium constant K is the product of K1 and K2. Okay. Next we come to the applications of the equilibrium constant. The first application is the extent of the reaction. If K is very large means it is greater than 10 to the power 3, the reaction proceeds to completion. If K value ranges from 10 to the power minus 3 to 10 to the power 3, or I can say K is approximately equals to 1, then the system is at equilibrium. If K is very small means its value is less than 10 to the power minus 3, then no product formation occurs, right? Next application is prediction of direction of a reaction. So that depends on the values of QC and Kc, right? So if QC is greater than Kc, backward reaction preferred. If QC is equals to Kc, the system is at equilibrium. If QC is less than Kc, forward reaction is preferred. So these are the following applications of the equilibrium constant. So that's it, class 11. Thank you.